All right, one last statement that I should have said before closing out the last video is that the beat frequency, if you have two frequencies, F1 and F2, the beat frequency is the subtraction of the two individual frequencies. All right, so that goes up there. So now, to close off this lecture, we'll talk about a classic phenomenon in physics, a Doppler effect. When an object that produces sound is in motion, the sound you hear is a result of both the sound produced by the source as well as the motion of the source itself. When a race car drives by, the tones produced from the engine or exhaust can be constant, while the sound you hear increases in pitch as it approaches and decreases as it recedes away from you. So you hear this, right? And so it's increasing as coming by you, and then it decreases in pitch as it has gone, as it's going away from you. Even though if you were in the car, it would be a constant, right? So what causes that? Why is that? Because the motion of the source is squishing the waves closer and closer together as it approaches you. So smaller wavelength, higher frequency, higher pitch, and adds more distance between wave crests as it recedes. So longer wavelength, lower frequency, and lower pitch, right? So if you're traveling forwards and you're creating a wave that's coming out from you, by traveling forward faster and faster, you're actually squishing the wave, the frequency of the wave that you're that's coming out of you, in front of you, if you can imagine that. The wave crests get shorter and shorter because even though you're pumping each wave crest out at the same time, the faster you go, the more you're catching up to the wave crest that just left you, that you just spit out. And so the next wave crest comes in an actual shorter distance to the one that came out before. I don't know if that's as easily imagined as it is in my head, but that's what helps me understand. And then the reverse of that, if you had waves coming out the back of you as you were running away, right? Wave crests coming out at regular intervals, right? Then as you're running, you're actually putting more distance as you speed up. You're putting more and more distance between these wave crests, like these little breadcrumbs that you're dropping at regular time intervals. But because you're putting distance into the equation, then you're increasing that distance. And so you get longer wavelength or lower frequency and lower pitch. And so that's the effect that happens with sound. So the actual object that's producing the sound is moving, and that's altering the amount of space between wave crests because it's a physical phenomenon. So it's moving through space, the physical world. So it affects it. So the general equation for determining the frequency a listener will hear, which we will say is FL. One of these days when I go to write, it won't be on eraser. And we're going to say, so this is the listener, L for listener, and we're going to say S from source, right? So the frequency that the listener hears is equal to V plus VL divided by V plus VS, frequency of the source. So notice that this equation accounts for the possibility of the listener having some velocity as well. Astronomers and astrophysicists will tell you that the Doppler effect is extremely useful in determining velocities of bodies in space. If you know the frequency of light that is being emitted by a body, you are getting a shifted frequency from this known source frequency. The Doppler effect immediately tells you how fast the body is traveling toward or away from us. Red shifted and blue shifted are commonly used phrases to describe a lower and higher frequency Doppler shift respectively, due to the motion of a body in the sky. Next lecture, we will pick up thinking about light with the study of optics, and it will be quite a shift from what we've been talking about in this granular wave description type lectures.